Hi friends, welcome to Engineering Clinic. This is Dr. Pradeep Kumar. So in this session we are going to see flying ad hoc networks using ns3. So we are going to simulate this flying ad hoc networks. So we have heard about so many things like mannets, vanets, and now we call it as fanets. So now this is what we are going to see. So the main purpose here is we are going to use the existing mobility models for three-dimensional mobility models. So 3D mobility models. So one such mobility model is implemented in ns3 is called as Gauss-Markov mobility model. So which comes with ns3. So this model only we are going to deploy and we are going to use flying ad hoc network simulation in ns3. So what I do is I have taken a source code like this. So first let me explain you the source code. So what my source code contains I will explain you, and so if you want to know line by line source code you can just refer my other videos, first.cc, second.cc and third.cc explanation. I will give it in the description link also. You can able to check those links. And now in this case I will just explain you. So we have totally have 20 nodes here, so 20 wireless nodes, and Wi-Fi helper, we have a Wi-Fi object, the standard of 802.11b. so we have A, B, G, N, there are so many models available. So we are going to use a MAC standard of 802.11b. in case if you want to use N also you can use, even the latest one Wi-Fi 6 also you can use. So the list are 802.11a is supported, 802.11b is supported, 802.11n is supported, 802.11ad CSE is supported, 802.11 AX is also supported. So apart from that, in N and AC we have two things, 2.4 gigahertz and 5 gigahertz also, both are being supported here. So ns3 supports all these stuffs for this Wi-Fi physical layer standard. You can use it. In case if you want to use 802.11p also supported. This is for vehicular networks. So we call VANETs, or it's called as wave. Wireless access in vehicular environments. That's what we called as waves. So this how the way this helper class is supported. So NQoS is no longer available in ns3.31. So we will just remove this NQ helper, and I'll create a simple object here. So this is the MAC. So we have a simple Wi-Fi MAC helper MAC. So then we have ad hoc Wi-Fi MAC. So in this we have again various things called as ad hoc Wi-Fi MAC. Then we have STA Wi-Fi MAC. We have AP Wi-Fi MAC. So ns3 supports this kind of MACs. So ad hoc Wi-Fi MAC is the MAC with all the nodes are in ad hoc mode, they can able to form the network. So this only we are going to use for flying ad hoc networks, because when the nodes are flying in the above the ground, so they will be talking to each other through without any infrastructure. So AP Wi-Fi MAC means we need to have a router for handling it. Station Wi-Fi MAC, this is also similar like ad hoc Wi-Fi MAC, but it will be used in the ground. So with the antenna will be pointing towards the ground. So that's how the way this stationed Wi-Fi MAC will work. Okay, so now we have this remote station manager. So constant rate Wi-Fi manager. So all of them will have a constant rate Wi-Fi manager. So here we have a data mode. So we have a rate of 54 Mbps. So the B standard supports 54 Mbps a maximum. So even if you want to have 12 Mbps, if you want to have 1 Mbps, we can able to set it. So ns3 have the support for all these things. Then we have a physical layer helper, or YANS. YANS means yet another network simulator. Then we have a channel. So in this channel we have two things, propagation loss model and propagation delay model. So constant speed propagation delay model and frisk propagation loss model. If you are from electronics background, you can refer the documentation of these two source codes, propagation loss and propagation delay models. Then we are creating a channel. So these are all channel properties. So once we create the channel, it's a communication path is established. Then the net device container. So the networking device, so which is a hardware and software combination of your networking device. So we are installing this on the physical layer of Wi-Fi PHY, then MAC, that's a MAC Wi-Fi MAC helper, and c is the number of nodes, so we can call it c dot create. So c is the number of nodes. So this is what we are doing. And enabling AO routing on all backbone nodes, so we are going to have enable AODV protocol. So AODV protocol is being used for FANETs as well. So in our examples we are going to use FANETs here. So that's how the way the AODV protocol we are using. So we can use other protocol as well, like DSR, OLSR, DSTV, all these protocols also we can use it, but in this example we are going to use only AODV. Then we have routing helper AODV and internet at install C. So we can install it on the all the nodes. C is number of nodes, node container. So totally 20 nodes it installed. Then we are setting the addresses for each and every node, 192.168.0.0, and the masking address is this, and creating a assigning this address to all the devices, C devices. C devices means, so what are the networking devices for all the devices? So we are installing this addresses here. Now comes the mobility model. So this is where the mobility model. So what it is given here is a 2D mobility model. I'll show you two things. First thing, I run with this existing model, then I'll change it to Gauss Markov mobility model. Okay. So now in this case what happens is we have a position allocator. So this is a 2-dimensional mobility model, 2D mobility model. So here mobility helper mobility, and we have a position allocator. So in the position allocator we have the minimum x, minimum y, and delta is a change in x and change in y. The grid width is 2 and row first. The name of the mobility model is random walk 2-dimensional mobility model. So we have a value of x and y, that is minus 100, 100, minus 100, 100. So this is how the way the x and y works. So maybe if you feel, for example, minus 100, 100 is one x and y. This is on the x-axis, for example, and on the y-axis we have. So let's say in the x-axis, when what we can see is, so this is the center. For example, if this is 0, so this side will be minus 100. So this is how the way the minus 100 works. On the other side we have a plus 100. So similarly in the y-axis also we can have minus 100 on this side, and plus 100 on this side, and the minus 100 on this side. So that means the nodes can move any direction from left to right. So that's how the way we are just planning it here. Okay, so this is what the 2 dimension, but we are making to run in 3 dimension also. Z axis also we are going to run. So that's what we will be seeing it. Then mobility dot install. So install this mobility pattern in all the nodes. So that is all the nodes. And the application what we are going to use, UDP packets. So the port number is number 9. We are starting the second set 1 and 10, and the first node get 0. The C dot get 0 means the C is the number of nodes. Get 0 means the first node. The 0th node will be the server, and the client will be the first node. Okay, so on this thing, and we are enabling the packet capture. So this is how the way things run. So we'll see the graphical user also. So network animation also will include. So first let me include the code for network animation. So here we have a include ns3 netanim module.h. So already it's included. So we have to include this, and when I come here I will just include animation interface anim. So the name is FANET example.xml. So this is an XML file. I am just including fanetx.xml. So this is the file that we are going to create. So this is what network animation using netanim. So the following line. Okay, now I need to create a ASCII trace file also. So in that case, ASCII trace helper. So name of the object I want to give it as ASCII. So this ASCII trace helper, we will be tracing the physical layer type. So in this we have a physical layer as Wi-Fi PHY. So just copy this variable, and then we can use dot enable ASCII all. So enable the ASCII for this Wi-Fi PHY. So the ASCII cannot be enabled for all the things. Since the physical layer is a channel, so we can able to create the ASCII. So then ASCII dot create file stream. So the name of the file I want to give it as fanetx.tr. Okay. So this is the trace file. So I have just enabled the ASCII trace matrix. ASCII trace matrix can be processed using trace metric software. So this is the way we can able to use this. So in this example we have seen a simple example. So if you want to know more about the entire coding, you can refer to the first 3 videos, first.cc, second.cc and third.cc. So you can understand better about the line by line understanding of the code. Okay, so after it is done, let me run this example. So I'll open the terminal. So let me store this file save as. I'll store it in the scratch folder. Downloads ns3.31 scratch. In this scratch I store it as wi-fi aodv.cc. This is a file I will be storing it. Now I will be running it. cd ns all-in-one cd ns3.31 /waf _run scratch wi-fi. So once I run this, so far no errors, so no errors are there. So now we can see we have this second these things. Just check the code here. Here we have the enable packet capture. So this is the Wireshark packet capture. So packet capture is enabled, so that's why all the file names coming with second. So let me use Wi-Fi. So I use fanet ex. So wherever it comes, I will change it to fanet ex. Okay. So now I will be running it again. So let me delete everything. rm star.pcap. Let me delete all the pcap files. So now we don't have any packet capture file. Now I will be running it. Okay, so now we can check it. So we can see all the fanet 11.0, 12.0, 13.0 like that. We got the files. So because we are enabling the packet capture for this Wi-Fi PHY, as well as we have enabled the packet capture for this ASCII for Wi-Fi PHY. So in the Wi-Fi PHY, between node 11.20, 12.20, 13.20, because 0 is a server. So all the clients, how they interact with the server. So that's how the way these packets are being generated. Okay, so now what I do is, I'll just show you any one of this file. So let me use 10 here. Okay, so Wireshark, and then fanetex -1-0.pcap. So you can see this is the Wireshark file that what we got it here, and you can see the statistics here. So what is the IO graph? So how the graph performs, packets per second, how many packets per second at what timing. So this will be listed out here. So you can able to check the packet level analysis here. So what happens to UDP packet, IP version 4, logic packet, then PHY layer. So all these stuffs you can able to check it here using this, and there are so many other information as well. You can able to check the complete summary of all these things. Okay, so this is on the Wireshark. Then let me go to the animation. So in the animation we have netanim. This I'll open it. The name of the file is fanetex.xml. Okay, so fanetex open. So far we are not doing any fanet here. We are just doing only, sorry, note number. Okay, I'll make the notes to size to this. Then I'll run it. So you can see the 20 nodes are moving here and there according to their distance. Okay, so that's how the way the nodes are moving here and there. So this is a simple animation that we can able to see, and we can able to check the ASCII file also. So gedit fanet.tr. So this is the ASCII file. So this is the ASCII trace what we got. So here in the ASCII trace, the first command is T means it is transmission, R means receiving, plus means NQ, minus means DQ. So D mean drop. So that's how the way the packets are exchanged between these nodes. Okay, so this can be processed using trace matrix, but trace matrix may not support all the protocols what we get it. It will support only some list of protocols. So accordingly the trace matrix will work out. So this is on a simple two-dimensional 3D model. Okay, so now the same case I am going to use 3 dimension here. Okay, so let me use Google for that, so that you can also easily can be able to do. So Gauss Markov model ns3, and you try it. So we have a Gauss Markov mobility model in ns3 somewhere here, not this, somewhere here, yeah. So this reference, you go to the Gauss Markov mobility model. So there we have a given an example here. So this is an example here. So from here to here I will just copy it here. So if you want, you can, if you are doing some research on flying ad hoc networks or mobility models, you can able to try this page, and there are so many other relevant pages as far as 3-dimensional mobility model. So this is the only protocol in ns3, only mobility model in ns3 that supports 3-dimension is Gauss Markov mobility model. Now what I do is, in this example I'll go to the mobility model code here. Okay, so first what I do is I'll just make it to commenting code. I'll just comment out from here up till here. Okay, so now what I do is I'll be using mobility model 3D. I'll use 3D here. So this is a 3D model and paste it here. So I just pasted it here. So the following is the 3D mobility model. So you can see that the mobility model, mobility helper mobility, the same variable name. Please use the same variable name whatever mentioned here, else you will have a confusion. I'll show you that also. So set mobility model ns3 Gauss Markov mobility model. See the bounds. So bound box value. So it is something like a 3-dimensional box. So 0 to 1,50,000 means around 1,500 kilometers. So that's what the box here. So let us go with a simple thing called as 100 meters. 0 to 100 meters, 100 meters, and 100 meters. So x-axis 100, y-axis 100, and z-axis 100. In case if you want, you can have this also, minus 100 also. You can have minus 100 to 100. So let me go with 0. So let's have the starting origin as 0. So time step is every time step 0.5 seconds. Alpha. So based on this parabolic, probability value only, the mobility, the nodes are moving. And mean velocity is minimum is 800 and maximum is 1200. So this also you can able to change the minimum velocity to a lesser value as well. Direction. So direction is minimum 0, maximum 6.28. This also direction. So you can able to refer the complete theory behind this Gauss Markov mobility model. Then mean pitch. So when the nodes are moving, so in what pitch they will be moving. So minimum and maximum, the pitch is given as constant 0.05. So this also if you want you can vary. Then normal velocity, normal direction, and normal pitch. So this is an average and this is the normal. So in the normal we have random variable. So starting from 0 the variance and the bound. So bound is 0.4 and based on the variance the value will be adjusted. So this is how the way the normal pitch works. Okay. So next thing is mobility position allocator. So how the position of the nodes will be placed. So again we have maximum 100. Here it is 100 and here also it is 100. So 100 cross 100 cross 100. You can see the cuboid, we call it as a cuboid, where all the sides are equal to 100 meters. So that means it is something like a 3-dimensional box. Within the box, the drones, the unmanned aerial vehicles, or the nodes of the flying ad hoc networks are just flying. Okay, so and mobility install Wi-Fi station node. So that's what the station node. So we will use the variable name C here. Okay, because we are using the C is the number of nodes here. Okay, so now the packets I will change it here. So FANETX Gauss, I will use FANET Gauss. Similarly, I can use Gauss and I can use Gauss here. Okay, so I have got these three names just renamed. So FANET Gauss, FANET example. FANET example refers to 2D and FANET Gauss refers 3D. Or else let me use 3D rather than it will be better to understand. FANET 3D. So the earlier example is FANET 2D. It's not FANET, it's simple MANETs. Okay, fine. So now I will be running this example again. Okay. So when I compile this example, you might be getting some errors as well. Okay, so no errors. So that means my program compiled successfully. Now you can see FANET 3D. Okay, so now FANET X also there in P capture. and FANET 3D also there in packet capture. Now I'll use the same thing here, FANET 3D 10. So Wireshark FANET 3D-1-0 dot pcap. So once you have this, you just go to the statistics here, IO graph. So you can see that after time 4 it was completely it's 1 only. So number of packets per second is simply 1, and total this also it's simple. But whereas in this case I'll open one more window, Wireshark FANET EX-1-0.pcap. Now we can see here the statistics involves, it is both same only, but only thing is the mobility model is changed. So now we can see that at time number 7 time units it was different. So this mobility model have a role on this packet. So it is only one packet after a period of time it is constant, because the nodes are flying in 3 dimension, but in this case the nodes are flying in 2 dimension, or not flying, the nodes are moving in 2 dimension, whereas in the 3D model it is just flying across. So this is how the way it works. So now I'll just close this. So let me go and open this in the NetAnim. So NetAnim. So in the NetAnim I'll just open this file, FANET 3D.xml. Yeah, so slightly different here. So let me use node number 10. So 10 nodes. So you see that they are just scattered in 3D models, and I'll remove the node ID as well. You can see, so they are just flying here and there. So according to the random position model, so the speed also differs from 800 to 1200 meters per second. So which is a very huge speed, but in case if you want to adjust the speed, you can able to adjust it. So even you can see the statistics of the each and every node. The node IP address also you can see. Yeah, now the simulation over. So since I have given only 10 seconds, the simulation gets over. Okay, so similarly the packet capture will give you the more information, and I'll show you the FANET 3D.tr, the trace file also. So this is a trace file. What we got is a trace file. So you can see the number of lines. The trace file somewhere around is 203 lines. The same way we have this FANET EX. In FANET EX it is around 208 lines. So it is 203 and 208 lines, and the various packets have been used the same way, but only thing is the statistics might be changing in the Wireshark. So Wireshark may have a major difference here. Maybe I'll just show you some more thing, 110-0 in pcap. So the statistics, can you see? So this is how the way it works. So 1 packets per second, then 2 packets per second, and it goes like this. And not only that, we can see other statistics as well. For example, packet length. So what are the different packet lengths here? So totally 10 packets from packet size of 80 to 159. So this comes here, and we have protocol hierarchy. So what are the different protocol hierarchy also? So how many percentage of bytes, how many bits per second for each and every protocol. So what is used in the particular packet type. So we can able to analyze so many other information as well, but you just refer the documentation of Wireshark to get more details on this particular help. So the purpose of this example is just to show you how it works in 3-dimensional mobility model. Okay, so then the trace file also done, and so in future we will have the another thing called as using OpenStreetMaps Sumo. Already we have a Sumo. So FANETs, so banners we already have. So that means if we use 3D model in the VANETs, it becomes FANETs. So flying cars, that's what we call as flying car simulation. So this also we can able to try, but we need more time to simulate these kind of networks. So this is how the way we can able to do the simulation here. So in future we will be doing this kind of simulation also in my YouTube channel here. So now in this example I have just explained you about the Gauss Markov mobility model. So thanks for watching and thanks for listening. If you want to plot any characteristics, graphs using flow metrics, all these things, you can just please refer my other videos relevant to ns3 tutorials in my channel. There are more than 25 video lectures available that categorizes all the performance metrics, all the graphical tools, all the performance tools are available for plotting. And please subscribe to my channel and share it to your friends. So thank you. Thanks for watching.